of Giulio's lectures on Poisson boundaries for random walks on groups.
Maybe Giulio can't hear us. Can you hear us, Giulio?
Giulio, yeah. Hi. Okay, he saw the waving at least. No, we don't hear you. Are you chatting with him?
Yeah, I'm writing to him privately. But he hasn't written back yet.
Can you hear me if I remove this?
Yeah, now we can hear you. Yeah.
Oh, so maybe it's the AirPods. Let me put them back on.
No.
Yeah, now yes, right?
Now, yes.
Awesome. Yeah. Okay. Sorry, guys. Okay, awesome.
Good, right. Well, let's start again. So, yeah, everyone ready for part 3 of Giulio's lectures on Poisson boundaries for random walks on groups.
Thank you, Harry, for the introduction. Thanks everybody who is still here. I understand it's a non-trivial, like the Poisson boundary of a free group, to be here after 3-4 days. So it's kind of okay. So the good news maybe is that today we are going to actually look at some more geometric applications. So if you bore with me yesterday with all this measure theory, today we're going to see much more geometry. And in fact, we're going to prove what Kazuo was alluding to before, that in fact for the Poisson boundary of a mapping class group, we could identify it with the sublinearly Morse boundary. So let me first start with some history or examples to see what it is known. So the general framework would be a group and some measure, and we definitely need, very important, that the entropy of the measure is finite, so H is the entropy. Otherwise, we can't do anything pretty much. And then some nice moment assumption. For instance, it has finite first moment. Or it could, if you have a finitely supported, it even simpler, so you can think of it like that. So, okay, what things are known about Poisson boundaries? Well, a lot has been known. So people started studying trivial boundaries. So people, even Blackwell in the 50s, I think, or 60s, started talking about harmonic functions and abelian groups. And basically, they proved that there's an any. So they didn't talk about Poisson boundary back then, but they proved that it's trivial. And then Ding and Molyutov proved it for nilpotent. I'm talking about discrete nilpotent groups. For Lie groups is a bit trickier, but anyways. And then eventually people started really defining this Poisson boundary and finding the first examples where it's not trivial. So we said, however, yesterday already that if the group is sub-exponential growth, we don't really have anything to say because the boundary is always trivial because the entropy must be 0. However, things get much more interesting when you go to non-amenable groups. So for non-amenable groups, so it's known that for non-amenable groups, the boundary is always non-trivial. So the entropy is always non-zero and the boundary is always non-trivial for basically any nice measure. On the other hand, when the group is amenable, there are measures for which the boundary is trivial.
Wait, sorry, not every group, right? Not all amenable groups, like ones which are not nilpotent.
No. I meant there exists a mu where the boundary is trivial. Sorry.
Yeah, I see.
yeah. Sorry. Yeah. So then, but yeah, that's right. So, but of course, yeah, for the amenable groups, there are lots of tricks, lots of subtleties. In fact, this statement that there exists always at least a measure where the boundary is trivial goes back to Kalmanovich and Vershik, so in the 80s. But then the actual characterizations of all the groups for which the boundary is trivial for all measures. Well, this came much more recently. In fact, basically came with this work of Fish, Hartman, Tamuz, and Lahidi Ferdozi, like just maybe 3 years ago. So really recent. Anyways, we're not going to be super concerned about this, except our groups will be basically always non-amenable. So we would already know that the boundary at least is non-trivial. But again, what is it? Also, it's interesting to remark relation between the vanishing of the entropy and the vanishing of the drift. This is the speed drift or speed of the walk. And for nice symmetric measures, basically these things are equivalent. So so for instance, in particular, you would imagine, so a corollary of this, you would say that if G is amenable, it's non-amenable, and it looks, and you look at the action of the group on itself, so on its Cayley graph, well, then the entropy, H infinity, is positive because the boundary is non-trivial. And then also the drift is also positive. This is the action of the group on itself. Now, it's much more tricky if you look at the much more degenerate action. For instance, if you look at the action of the mapping class group, not on itself, but say on the Cayley graph, on the curve complex, not on the Cayley graph, but on the curve complex, well, then it's much more subtle because this space is much bigger, and somehow the action is very bad, it's non-proper and things like this. So in fact, this I proved with Joseph, but this is a much more subtle question. But if you look at the group acting on itself, the non-availability is sufficient to detect the positivity of this. Okay, so this is a bit of a general context. The groups we care more about are groups where we have some hyperbolic properties or hyperbolic directions. So for instance, just hyperbolic groups themselves. So if you have a hyperbolic group acting on itself, you clearly have the Gromov boundary. And the theorem of Kajmanovic that we will actually basically prove or sketch the proof thereof soon says that the Gromov boundary with the hidden measure is indeed a model for the Poisson boundary. So again, this is the action of the group on itself. So the drift, we already know it's positive, well, unless the group is virtually cyclic, in which case the boundary is trivial. But if the group is a non-elementary hyperbolic group, well, the drift, we already know it's positive, so we already know the boundary is trivial. And the hyperbolic case, this is basically enough to tell you what the Poisson boundary is. So I will explain. People have looked at relatively hyperbolic groups. There's several people, I think Gattaro and Matteus were the first ones. And in fact, later I will give an application of our theory so you could identify a boundary of a relatively hyperbolic group also with the sublinearly Morse boundary. So this one also will be discussed later today. And then what about other non-positively curved spaces, for instance, cat-zero spaces? Well, for cat-zero spaces, you have the visual boundary. And basically, under nice conditions, so you will see that the natural boundary here would be the visual boundary. And by Carlson and Margulis' work, basically you can prove this sublinearly tracking property for actions on cat-zero spaces, and then you could get the Poisson boundary at the visual boundary. Any questions so far? I'm going fast, assuming that you already heard at least about some of these groups. Of course, you cannot learn everything about these groups in 1 minute. Now let's look at maybe our favorite example would be the mapping class group. So the mapping class group has many actions. And so for different actions, you get potentially different boundaries, even though, of course, in the end, as a G space, as a space with a measure and a group action, they must be equivalent because the Poisson boundary just depends on the group and on the measure. But so the first action that was considered is the action on Teichmuller space, which of course is not hyperbolic, but it's a proper space. And in that case, by work of Kajmanovic and Mazur, you can identify the boundary of the group with the boundary of the space, so with PML. So the Thurston boundary. However, this is a sort of somewhat relying on Teichmuller theory. So in a sense, it's not super intrinsic to the mapping class group. Then Joseph and I looked at this other action, the action on the curve complex. And then, of course, the curve complex is, so this one is a curve complex. Maybe I should write the definition, not the definition, but at least explain what my notation is. So curve complex would be this. By the way, I'm sorry, Kazura, my mapping class group would be mod S. I know you don't like it, but anyways. So the curve complex would be COS. And the curve complex is hyperbolic, but non-proper. So you see, this is nice in one sense, but the action is kind of bad, but it still has a Gromov boundary. So this one would be the, you see, this would be the Gromov boundary. And so if you take the Gromov boundary of the curve complex, you can also identify it with the boundary of the mapping class group. And this is because this action is bad, but it's acylindrical. And so you have still some properness. But what we're interested in today is the third case. So the third case is the action of, in some sense, the most intrinsic. I mean, it's the action of the group on itself. And so the action on the group of itself is nice, of course, very, very proper. But the problem is that the boundary of this group as a Cayley graph, well, is hard to define in general because this is not hyperbolic and you know it's not cat zero and you don't know what to do. And so for this reason, we came up with the sublinearly most boundary. And in fact, in the end, so I will, in fact, the main thing I want to do later is to give a sketch of the proof that in fact you do have identification of the sublinearly most boundary of the mapping class group with its Poisson boundary. So this is the work with Yolan and Kaja. Now, if you want to go beyond the mapping class group, of course, the next group is out FN. So out FN, well, has been studied by Camille Horbez for when you look at the action on the out FN on the outer space. So it's the analog of the action of the Teichmuller space, basically. And you can prove the identification of the Poisson boundary on the boundary of outer space. Also, you could look at the analog of the curve complex, and in fact, you could look at, say, the free factor complex. So, and in that case, you can apply so this again is a hyperbolic situation, but not not proper. And in this case, the boundary of that, so you would be again the hyperbolic boundary of let's call it, I don't know, Fn, the free factor complex. And this also follows from my work with Joseph, because in general, in this case, we dealt with this case when you have any group acting on a hyperbolic proper, maybe non-proper space, as long as you have at least one WPD element. So this is related to what Abdul asked yesterday. So the action need not be acylindrical. This was in the first paper, but in fact, in the second paper, we just require that there's one hyperbolic WPD element. And that's because, again, the usual problem with the algorithmic theory is that if you see one WPD element once, and this gives you some properness, you will see it infinitely many times along your sample path, and that fortunately gives you enough properness to estimate this entry. So this is however, this would be another talk. Okay, so these are all more or less the of most groups that at least I care about. You guys might care about other groups, but are there any questions about this general situation? Okay, if not, maybe I can state at least one of the main theorems. So this is a pretty general theorem that we have with Yolan Kajro, and also contribution from Ilya, is a general identification criteria for Poisson boundaries with the sublinearly Morse boundary. So So, okay, so you start with just any finitely generated group and you take its scalar graph and you take a measure with finite first moment. So the first thing you have to suppose is that the support of the measure generates a non-amenable group. Again, it's true in the cases that we care about, and this because we do want to consider, we do want some this drift of the work to be positive. And then we take some sublinear function, concave sublinear function, as Kazura explained. And the only criteria that we need is a sublinear tracking criterion for couple Morse geodesics. So basically, the idea is you want to say that almost every simple path tracks sublinearly a couple Morse geodesic. And that's enough to guarantee both things that we need to identify the Poisson boundary. So, right, so we have our good old simple path. And before I talked about, so, okay, this point does not exist yet because we haven't created it yet, but we have a simple path and we have that, we have a geodesic or quasi-geodesic, even quasi-geodesic would be nice actually. So that this quasi-geodesic is couple Morse with this specific count. And if it sublinearly tracks, let me see. Yeah, I guess probably you need the rate to be also couple. Sorry, I guess I guess I didn't write it. Yeah, I think I forgot. Yeah. So the kappa, yeah. So the kappa I think you get is the worst between the kappa of the geodesic and the rate.
I don't know if you get the same kappa, but yeah, then just I guess you can take the maximum or something. Is that what you're saying?
Yeah, exactly.
Yeah, but yeah, I mean, in our case, it will be different kappas. Right? Yeah, one of them is log, one of them is log to some.
Yeah, different. Yeah, of course, the different groups will have different kappa. That's for sure. Yeah. Okay, so if you have these two things, what happens is that first of all, the sample path converges to your kappa boundary. And secondly, indeed, the sublinear tracking property will tell you that this boundary with this measure is indeed a model for the Poisson. So this is general criteria, and it's not hard, in fact, to prove once you set it up like this. It follows pretty closely from the sublinear tracking criterion that I mentioned yesterday, and I will explain more about that.
Is it important that X is a Cayley graph?
No, I don't think so.
Like if it's
so
a geometric action, yeah.
Yeah, geometric action would do it, I think. Yeah. Okay, so the two applications that we have, again, you could in principle apply this theorem to your favorite group, but you still need to prove this sublinear tracking property. So the two applications that we have is with the relatively hyperbolic group. So in that case, we take kappa to be log, just log t. And if you take a finitely supported measure on your group, okay, your group is relatively hyperbolic and also in some sense non-elementary, maybe non-amenable for sure. And so you can use this logarithmic function as your tracking rate, and this would work, and it would give you an identification of your Poisson boundary with the kappa boundary. And the other situation is it's similar, but slightly more technical, which would be for the mapping class group. So you start with a mapping class group of a surface with genus G and B punctures, and we use kappa to be log p of t. So the pth power of the logarithm, where p is the complexity of the surface. And the reason why we care about the complexity will be clear when I tell you the sketch of the proof, because this is the depth of the hierarchy associated to this mapping class group. So we will use the subsurface projections to prove this result, and you will have to prove some tracking result at every level of your hierarchy, and you get the log out of every level of the hierarchy. And then in the end, you're gonna get logarithm, the power of the log. In fact, from the proof, you will see pretty clearly that basically the same strategy applies, say, for hierarchically hyperbolic groups. So we didn't write it in that generality, but you will see that the ingredients are there, so that should not be very different. Okay, so this would be yeah. So those would be the main theories. So okay, so maybe let's recall and explore a little bit more, because I just mentioned this at the very end of yesterday's talk. Why linear tracking property is sufficient to tell you the identification of the Poisson boundary. So in general, as I mentioned before, so if you know that you have certain modification of your space, and you know both that your walk converges almost surely, and also you know that for almost every boundary point, there is a geodesic or quasi-geodesic ray which tracks sublinearly the path, so the distance between the path, the sample path, and the geodesic at the correct time. So L is the drift. So if gamma is parameterized by arc length, it makes sense that after n steps, your distance is roughly L times n. So that's why I put this L times n, just to find the right point on the geodesic. So if you have such a tracking property, then indeed this boundary that you have is a model for the Poisson. And so the idea is indeed using the entropy criterion that I mentioned yesterday, in particular this conditional or relative entropy criterion. So the point is to show, recall, that the Kamenovich theorem said that the boundary that you have is the Poisson boundary. This is equivalent to say that for almost every boundary point, if you consider the entropy, let's say H infinity, of the conditional measure, so you take the condition around the walk, so let's call it P psi. You look at all the paths from the origin to psi, you restrict to that is also a stochastic process. It's not quite around the walk, but it's also still Markov chain, and you can associate the entropy. And the idea is that if the entropy is 0 for every point, means that you cannot split further this boundary. And so this boundary that you have is the right one, is the Poisson boundary. Because of course, whenever you have a path that converges to the boundary, well, you already know that the Poisson boundary will be so this would be a quotient of the Poisson boundary. So the Poisson boundary is the maximal boundary in the sense that is the one that has the most points, of course, but the problem is to define points is really hard. So this is what discussed yesterday. Okay, but now geometrically you could see if the action also, is not too non-proper, so it's proper, and also in a ball of radius r, there's at most an exponential number of points in the group orbit, then we can estimate the entropy, and you can do it more precisely, but let me, so I'm slightly cheating, giving you some sketch, but basically what happens is this. So you fix this point psi, and you want to look at what are all the possible locations of the walk. If you have a sublinear tracking property, it means that where do you find the location of the walk? Well, if you pick a point on the geodesic in the right point, and you draw a ball with a radius which is sublinear at this rate, then, well, it's very likely to find the path of your walk in here. So there's many paths that go to psi, but they all stay kind of close to this point of the geodesic. And so that's precisely the trick. So, and then you just estimate the entropy of this. But the entropy, well, if you're willing to get a little bit about the possibility that in fact not all points in fact align this pole, because with small probability they could still lie outside, and that creates a bit of a problem when you actually try to do the computation. But the idea of the proof is this. So you take the support of this measure, this conditional walk, is contained in this ball, and this ball has the radius, which is basically the distance between the end step and the geodesic, and this grows sublinear. And and remember, we have action is exponentially bounded growth. So remember that the number of elements that are in a ball of radius r grows sort of exponentially, at most exponentially. So how many elements there are in this ball? Well, they're exponential to the radius, and the radius is sublinear. And so in the end, the number of elements you get is sub-exponential. So that's basically the idea. So you can make it more precise, but I think that's an important point, that somehow the sublinear tracking property tells you that the entropy is, the relative entropy is small, and in fact it has to be zero for everything. Any questions? Am I going too fast? Too slow? Okay, so from here, you can see why this is necessary. And so this is basically when we want to look at this theorem that I mentioned, this general criteria. Basically, there's two things that you have to prove, right? So we had that almost every simple path sublinearly tracks a Kappa-Morse geodesic. So the first thing you have to prove is that if a path sublinearly tracks a Kappa-Morse geodesic, it does converge in this Kappa-Morse boundary to this geodesic. And then the second, that you have the sublinear tracking, and this is explained. So in that, then you do have. Okay. So yeah, I thought, yeah, let me skip this. I wanted to give you also an idea why this works on hyperbolic groups, but maybe it's just too much. So let's skip to the mapping. So in general, in fact, so the convergence is so there are two geometric lemmas that we're going to use, and maybe they were discussed somehow, or some version thereof were discussed in Kazer's talk. So the idea, so the first lemma is how do we prove convergence? Well, basically, you would just say that if you have a sequence of paths, you have a path in infinite geodesic, and then you just have a sequence of points. This would be any sequence of points, n plus 1, n plus 2, and so forth. And you just want to say that, well, if you know that the distance between these points and this geodesic is sublinear with this rate kappa, sublinear with respect to what? Well, to respect to the norm of xn, which the norm of xn, remember, is the distance from the origin. So to be the norm. So if you have that, the distance from the geodesic is at most kappa times the distance from the origin, then you can look at this definition of topology Gazura gave, and you would see that this is precisely compatible with the definition of topology. So this would imply indeed that this converges to gamma. Let's say not C. I want to say gamma or class, maybe class of gamma in this kappa bar. Okay. So now let's focus on the mapping class group. So in the mapping class group, we have to use this hierarchy machinery to estimate what happens to this distance between the sample path and the GNS. So recall what are the main points. So there's this. So we start with the surface, and we have various objects associated to it. So we have the curve complex of the surface, which again is a nice hyperbolic space. And we call ds the distance in this complex. And this complex has a Gromov boundary, which is also described. So it's describable as the space of n laminations. But in any case, we don't care too much about the specifics of that identification, but we know that this has a nice Gromov boundary. And then whenever you have a subsurface of your surface, you always have another curve complex, the curve complex of the subsurface. Right? And this has some distance, and also it's hyperbolic. Okay, and whenever you start with 2 points in the mapping class group or in the Cayley graph of the mapping class group, well, we can pick a path between x and y, but not just any path. By the theory of Mason-Minsky, we can always pick a hierarchy path. So it's a particular choice of quasi-geodesic that somewhat doesn't backtrack too much. And then you can project this hierarchy path to the curve complex, and also you get some, well, unparameterized quasi-geodesic. And what's nice is that in the end, we're going to be able to control this random walk on the mapping class group by controlling all the projections. And in particular, we control the projection to the curve complex of the whole surface, so C of S will be the most important part, will be the driving force. Okay, so what is the property that we're looking at? What kind of subset of the whole boundary we're looking at? Well, basically, what we want to look at this space where the projections are all logarithmic. So we call this space of laminations with the logarithmically bounded projection. So what is the space? Well, it's you take this infinite path, and then you want that the projection to each subsurface, well, is controlled by the log distance in the big curve complex between the origin and the subsurface. So, of course, you have to you know that points in the curve complex are curves. So if you pick a point here, this, you know, the boundary of your subsurface is some curve, and this tells you how far you can go in that particular subsurface. That's the basic idea. And you want to go somewhat logarithmically far depending on this distance. So in that sense, I'm saying that the distance in the curve complex of S controls everything. Also, we have this other notion of cloud. So I think we call this a cloud. So if you have a point in the mapping class group, well, there's some notion, of course, of projection. So you can project not just to the big curve complex, but you can project to I don't know, the curve complex of Y, for instance, where Y is some other subset. And so what is the point here? So the point is you want to pick, you want to pick this point in the mapping class groups so that when you project it to each subsurfaces, they're close to the geodesic. So somehow if you start with the ray in C of S, you can lift it to the mapping class group, but okay, you can't lift it uniquely, so you have different choices. So we have this notion of clause that basically tells you how to lift. So what are all the possible lifts of this geodesic? Of gamma. So this is all the machinery that we need. Any questions?
This cloud is just the same as the convex hull, right? In the of the set or something. Yeah.
Convex hull no, the cloud lives in the mapping class group, and this geodesic 0 to psi lives in the curve complex. So it's like a lift, but yeah, you can't. There's more than one ways to lift it. Yeah. But of course, the random walk starts in the mapping class group, so you can project everywhere and look at how the different projections. Okay, so the second geometric lemma that we need, that again, I hope Kazra gave some intuition or some similar lemma. So if you have a hierarchy path that has these logarithmically bounded projections, then this indeed is kappa contracting. Well, kappa here, yeah. And what is kappa here? Yeah, the kappa here is indeed log R to the 5th power. And so that is pretty much some application of the distance formula in some sense. So this is the second thing that we want. So basically what we want to show is that the random walks we are generically in this set, in this cloud with logarithmically bounded projection. That is basically the gist of what we want to do.
Did you tell? Maybe I missed it. Did you tell us what a resolution is of a hierarchy path?
Oh, resolution of a hierarchy path is just, well, I'm not really an expert, but yeah, it's basically a choice of a quasi-geodesic in this hierarchy. Let's respect this hierarchy. So because there's more than one choice. Kazra, you want to say more precisely?
Yeah, but maybe a hierarchy is like a bunch of geodesics in different curve graphs, right? So it's not really a path in the mapping class group. So you want to pick a path in the mapping class group whose shadow to each of those curve graphs moves forward along those geodesics, right? And then there's, so there's non-uniqueness. If you have two disjoint subsurfaces, you could just do this one first or the other one first. So a choice of a quasi-geodesic that is moving forward a straight line in each of those things is called a resolution of the hierarchy.
So it's just a different hierarchy path, right? Is that
it's also the same as hierarchy path. Yeah, right. That's right. So hierarchy is kind of the structure of all this wheels upon wheels of geodesics, and the resolution is a particular choice, that a path that actually does the correct thing in every subsurface. Yeah.
Thank you.
Yeah, so perhaps I should write is the resolution of a hierarchy. Yeah, exactly. Yeah. So that would be the most. So G is a resolution of the hierarchy. So it's a quasi-geodesic that respects the hierarchy. Okay. Okay, so now if we assume this this geometric properties, we can do some probability and prove this convergence result for them. So there are several steps. So what is the first step? So the first step is the following. So you want to say again that you have, yeah, you have your path, and you, in fact, remember that you already know because of, for instance, Joseph's work, that if you take the random walk in the curve complex, the random walk does converge to the boundary of the curve complex because the curve complex is hyperbolic. So there is a boundary point. And so if you look at in the main curve complex, you're gonna see that this path does indeed converge. And then, but on the other hand, you want to also project it to the other subsurfaces. And so what do you want to say? Well, you want to say that the progress that is made in the other subsurfaces is only logarithmic. So if you take this picture, but instead of taking it in the main curve complex, we take it in the secondary ones, this distance would only be logarithmic. So in y, but however, it would be linear in S. So in the main level, it's going to be linear, but in the other levels, it's going to be logarithmic. Okay, so and this is a nice idea that we sort of got from the paper of Sister and Taylor, where the idea is you combine the linear progress with the bounded geodesic image theorem. So what does the bounded geodesic image theorem say? Well, it tells you that if you're making progress in a subsurface, well, the only way to make progress in a subsurface is that if you look at it in the main curve complex, you must have that your path passes close to the boundary of y, right? So you always have two pictures here. So we have a picture in CS and a picture in CY. So we have to always compare these two pictures. So if you take 2 points here, X and Y, and you look at it in the other complex, well, the only way for the picture to make progress in CY is at some point the geodesic in CS passes close to the boundary of Y. Otherwise, you're not going to make it. Right? So, and in fact, even if you have a path, if you go from X to, before you enter in a neighborhood of a boundary of Y, you're not making any progress here. And then you make all the progress when you're near a boundary of Y. And then after the boundary of Y, you again don't make any progress. On the other hand, what does the linear progress say? Well, the linear progress says that this walk has positive drift, so it always goes forward. So it cannot spend too much time close to the boundary of Y. And so if it doesn't spend too much time close to the boundary of Y, it cannot make too much progress in Y. That's the basic idea. And we can make it precise. This step is somewhat easy to prove in a more formal way. So you see, you need linear progress with exponential decay. So the probability that you're less than some constant time n is indeed the decaying exponential. Whenever L has to be smaller than the drift. For instance, okay, maybe the best way, the most simple statement would be if you take the half of the drift, the probability that your progress is half of the drift times n, it decays exponentially fast. And so this is I think in this context of a mapping class group is already proven by Marr when you have a finitely supported measure. And then, well, in fact, more recently, people have done this for measures with, say, exponential first moment, but this is another story. So, okay, so basically what you do is you just say, okay, so if you set n to be log n, essentially, well, the probability that after log n time, you're not making any progress, you have a progress, you make constant progress, well, this is very, very small. So, and if you plug in log n in this expression, you get a polynomial. So this is the case polynomial. So the probability that in logarithmic time, you make no progress at all, the case polynomial. But the power of the polynomial, we can choose, we can tune by somehow choosing the constant in front of the log. Okay, and so basically the picture is what I said before. So the picture is this. So you look at you have your walk from y1 to wn, and yeah, and you have your boundary of y somewhere, and so you have your path. This path is at some point at time I1 gets close to boundary y, maybe. Then maybe there's something, and eventually maybe it may come back to another time I2, but then after I2 it never comes back. So all the progress has to occur in this area, so in this time. If you look at the progress in Y. But how much time are you gonna spend there? Well, precisely by what I said. So you're only gonna spend logarithmic time in this. So somehow all this is interesting because you're using these hyperbolicity properties, but you're not really using too many specifics of the mapping class group, except for this hyperbolicity and the bounded geodesic image scheme that does indeed play a big role. And so in the end, what are you gonna do? So if I fix this two, I have from 1 to n, if I fix this I1 and I2, well, I can estimate the probability that the distance between Wi and W2 is bigger than the log n. So you say the probability that, you see, that the supremum over y of dy. So you see, with CS, you control all the projections at once. So that's kind of the nice thing. So the probability that this is bigger than the log is less than n to the minus a over c. And now you just say, okay, you can choose all possible choices of I1 and all possible choices of I2. Okay, these are numbers from 1 to n, so you have n choices for I1 and n choices for I2. You have choose. So you have a quadratic factor. Okay, doesn't matter. So in the end, what is interesting is you get a polynomial factor here, polynomial bound. And if you choose a very large, we can make this polynomial very small. So we make the power very negative. And in fact, we need to make this power very negative because in the end, we want to apply the Boret-Fontaine limit. Okay, so that's the first point. The second point is somewhat similar, but kind of also somehow more tricky, but it also plays with this idea. So the other thing you have projections. It's tricky to define a projection in mapping class group, right? So, but in each curve complex, you can project points to quasi-geodesic because they're all hyperbolic spaces. So you could take the closest point projection in each of them. And so we call the projection of Wn to gamma, we call it Cn. However, in fact, in the mapping class group, we still need one property that follows from work of Askin and Rafi, where there exists a notion of projection. So basically, you can pick a point. If I give you 3 points in the mapping class group, there exists a notion of basically barycenter of these 3 points, so that it projects to the barycenter of the projections in all the curve complexes. So you can also make a choice of projection which is somehow uniform by making sure that every time you project to each individual curve complex, you get the right projection. So once you have this, then you can play this game that I outlined here. So we want to show, right? So we want to show that so there's two. Yeah, so this is the longer term goal, but let's look at the shorter term goal. Shorter term goal is to show that the probability that the distance between this end step and its projection is also at most logarithmic. And the trick here again is using the bounded geodesic image theorem. So actually, let's see whether we can guess what happens here. So let's cancel the hints. Let's see whether we can guess what should happen. Oops. So suppose that you do make a lot of progress in CY from Wn to Cn. Well, by the bounded geodesic image theorem, this is only possible if the geodesic segment, this one, passes close to boundary of Y. But the other interesting thing is that, well, we can control the distances because this walk makes linear progress. So this distance is roughly n in the big curve complex. This distance is roughly n in the big curve complex. And so this tells us that basically, yeah, and also we also know that we have a tracking property in the main curve graph. So we know that the distance between the geodesic and the path is about log n. So all this just by hyperbolicity of the big graph. And so if this is true, what happens is that if this segment is close to the boundary of Y, well, this other segment, the segment from 2n to C2n, cannot be also close to here, because there is this big linear gap between them. And so that's pretty useful because it tells us that in the other graph, CY, well, not making progress from 2n to C2n, so this is of 1. And so what is the other thing that we knew? Well, we know that because we proved just before that the progress you can make from 0 to Wn is at most log n, and also from Wn to 2n is the same, so it's also at most log n. And when you project, so this is a hyperbolic graph, so when you project, the closest point projection is course distance, is distance non-increasing basically, and so the distance between the two projections is also roughly log n. And so by by the triangle inequality, the distance between these two is at most this one plus this one plus this one. And so it's at most log n. So this is what we get out of looking at this diagram. This is at most. So you can play this game. You alternate looking at C of S and C of Y, and you look at the progress in one and in the other, and you have enough information, and you combine with this bounded geodesic image. Many questions. Maybe it's not easy to follow these steps because there's many steps. Okay, so and now let's go to this other claim, which is also a which is this consequence of this is that, well, look at the distance in the you make in Y from 1 to Wn. Well, this is not going to be usually it's not going to be bigger than the log of the distance in S between 1 and Wn. I mean, the idea is basically this is basically linear. In fact, this is basically n. So yeah, so I think that's yeah. So this one, yeah. So yeah, so this one just follows from the step one, in fact, because here we had a comparison between the progress between 1 and Wn and log n, and here we have a comparison between the log between the progress in Y and just the distance between 1 and Wn. This is basically its log. So we are getting closer to proving that this path indeed lie in this logarithmically bounded cloud. Okay, so now there's a trick that everybody, yeah, I guess this would be the step 3. So this is a first trick that everybody likes when you apply Morel can tell you. So you know that the probability of some event is less than a polynomial, right? So we first knew from the previous step that the probability that the supremum was, I don't know, bigger than C log n was smaller than n to some power. And in fact, we can choose this power to be -2. So which basically we can choose this constant here so that this power here is -2. And then the sum converges, and then we can just apply Borel. And so it says that almost surely you're going to see the opposite. So almost surely after some time, your projections will have at most logarithmically bounded projection in all subsurfaces, except the main one. And then, yeah, this is the discussion that I said before. So basically, if you know that the drift is positive, well, you know that you can replace n by the distance in the main curve graph. The distance in the main curve graph is basically n. So this. Okay. So we have basically proved that this converges to a couple most geodesic. And the reason is, well, the reason is because it's precisely this criteria that we said before. So if we know that our limited geodesic has the property that the excursions in every other subsurface is logarithmically bounded by the progress in the main subsurface, then this would immediately imply that this geodesic will converge to some point in this logarithmically bounded cloud. And then we have to use this geometric lemma that we mentioned before, that if you are in this logarithmically bounded cloud, then the limit is kappa contracting and source is kappa Morse. That's the basic idea. Any questions?
Hey, I might be misunderstanding this, but previously when we were trying to bound the distance between gamma and the sample path.
Not yet.
Oh, never mind.
So that's the last step. Yeah. So
okay.
Yeah. So this just says that this path converges, and the limit is in this nice cloud. So the limit in geodesic processes this logarithmic bounds. Now the distance between the geodesic and the sample path will be in fact bounded in the next step. Yeah. Of course, they're related, these questions, but yeah. So the last point is indeed this one. And that's basically really an application of the distance formula. So you see that you know, so we proved that the distance between the end step of the walk and this projection is bounded logarithmically in each subsurface. And so from here, including the main subsurface. And so from here, we can use the distance formula. So we know that the distance in the mapping class group is given by the sum of all the subsurfaces. When maybe we have some cutoff here. Of course, this sum there's infinitely many subsurfaces. So in principle, it's impossible to apply. But you also have to remember this geodesic image theorem, that not many subsurfaces can be active at the same time. So in this contribution, only some of them are active. Right? So in particular, right? So if you make a logarithmic progress from x to y, so suppose this is log n, well, you can be close to logarithmically many subsurfaces, y1, y2, blah, 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 y log n. Yeah. And so you can make progress in these ones. And then, but how much progress can you make? Well, if you look at y1, well, you only make progress when you're close to here, and from here to here, you don't make any progress, and from here to here, you don't make any progress. So you make the progress in this part. And then, but you also know that this progress is logarithmic. So in fact, in a relatively hyperbolic groups, you're done because there's only one level of hierarchy. You are either in the main, in the Kondorf space, or you are in the peripheral, and then you also make log n progress in the peripheral. For the mapping class group is more complicated because you can have nested sequences of subsurfaces. So Y can have another subsurface Z, right? And then you have to look at this again. And you can make progress in Z, also logarithmic progress in Z. But then you see that what matters is the depth of the hierarchy. And the depth is indeed P is the complexity. P is 3G minus 3. So this is a calculation with the distance formula. So you see that you have contribution of log n at the main level, and then you have contribution of log n at each level recursively. But you have P levels. So in the end, you don't get log n to the P, but you get log n to the P plus. But still, you can put all this together, and you get this estimate in the Cayley graph of the mapping class group. So in the end, you indeed prove that the tracking property, right? So in the end, you prove that for almost every sample path, there exists this resolution of this hierarchy G, resolution of a hierarchy in mod S, such that, well, the distance between the n step in the mapping class group, so dg, let's say the Cayley graph distance between this divided by log p plus 1. Yeah, is bounded. Yeah. So let's say the length soup of this is bounded. So definitely sublinear, and in fact, we have a precise estimate, which is of this order. So clearly from here, we get everything, because from here, we get that. Yeah, so then almost every, and moreover, the other thing that you get is that G is indeed kappa Morse. So almost every sample path sublinearly tracks a kappa Morse quasi-geodesic. And then, of course, the next corollary is what we're really after, is that the random walk converges to kappa Morse almost surely. And the boundary with the hidden measure is a model of the Poisson. So that's basically the sketch of the whole proof. Of course, well, one needs to go more in detail to understand better all the details, but that's the basic idea. And again, so I also want to put two further remarks. So, okay, so the other remark is that, okay, first one is for relatively hyperbolic groups, you basically have the same proof. But you don't need this, the depth of the hierarchy is 1. So you just do with kappa r to be log r. The other thing which is also interesting is that this bound improves on the previous bounds on the mapping class group. So I think there's a paper of Sisto where he proves some statement like this, where you, of course, there's no sublinearly Morse boundary, but just in the tracking rate. So he says that there's a geodesic which tracks the random walk on the mapping class group, but his rate is worse than ours. So his rate is like square root of n log n. So in fact, he already proves the tracking, log r tracking also for relatively hyperbolic groups. So in fact, yeah, so he proves that at least the same tracking result, but then for the mapping class group, yeah, this analysis gives you better bound because we can just get the power of the logarithm rather than this square root. Yeah, so he proves that this is bound. Okay, so yeah, I think even if I have 5 more minutes, I think I will not give you more details, but I will leave it here. So yeah, so anyways, so thank you for coming to this mini course. I hope you learned something. Otherwise, I can answer some of your questions. Thank you.
Great. Let's thank Giulio. And yeah, does anybody have any questions? So what was the reference that you gave at some point for the barycenter of points in mapping class group? Because I'm used to that being a Bairstock and Minsky thing, but was this one slightly different?
Right. So the barycenter construction that I know of, I was referring to asking Rafi, maybe Kaza tells better.
Yeah, also Mazer, when we proved this the rigidity of the Teichmüller space, like and before that, the actually paper before that, which we proved that the rank of the Teichmüller space and mapping class group is some number, like it's the geometric rank. So the idea is that you project everything into the curve graphs. Like you pick 3 points, you project into each curve graph, then each of them is hyperbolic, so you can look at the center of those triangles in each of the curve graphs, and then you have to prove those guys are actually consistent, so they satisfy this Bairstock inequality. So which means there's a realization, you can put them together and then bring it back up.
So why is this different to the thing that's in Bairstock-Minsky?
I'm not sure if it's I'm not sure if they do it exactly like that. It's possible we do it for Teichmüller and for mapping class at the same time.
Oh,
not
yeah, sure. Okay. They're just doing it for mapping class group, I think. So
yeah, I mean, it's unclear if.
Yeah. Okay. Probably, maybe it's
the idea is definitely exists.
I think the main distinction is that like Teichmüller space with respect to like all the subsurfaces, it's not an HHS, like and right, is that maybe one of the.
Well, I mean, yeah, this is not a new paper. Yeah, I mean, so right. I mean, this stuff is done in the general notion of HHS now, for sure. Right? But I think some version of this is also done in Bairstock. I don't know if they do this take the barycenter realization thing. I'm not sure if they do that, but maybe they do. Yeah,
I thought that's not what it was, but maybe.
Yeah,
maybe
no, it's possible.
Yeah.
It's very possible. Yeah.
Okay, but yeah, they're just doing mapping class group. They're not doing Teich, I think. So.
No, I mean, like, no, the idea is kind of like clear. Like, you can take barycenter in each H2, but then what you get at the end is actually consistent, so you can realize it as an mapping class group.
So how do you, in Teichmüller space, how do you get the realization? Do you use,
well, it's the same. It's a kind of the same thing, right? But you have this annuli guy, which are different. So the projection to annuli are just you project to the horoball associated to annulus. So it's no longer like for a curve graph of the annulus is a line, but the curve graph of an annulus for a Teichmüller space is like a horoball in H2, but it's still hyperbolic. So every 3 points still have a center of mass, and then you can use that to do realization. Yeah.
Okay. Cool.
So you have to prove those are consistent, so you can still do it. Yeah, and then you do realization. I mean, yeah, you have to prove this realization theorem for Teichmüller space. Yeah, maybe that's the difference.
Yeah.
But it's all the same